Hello, and welcome to this lecture about decision trees. In this lecture, you will learn about the Decision Tree Classifier, Regression Tree for doing regression, and Random Forest, which is basically an ensemble of several decision trees. Let's start by defining a simple dataset that we will use as an example in this lecture. Suppose that we want to collect data in order to predict if one can swim or not, depending on two features. The first one is the time of the year, basically the month of the year, so from 1 to 12. And the second feature is the latitude. So values here indicate that we are towards the North Pole, and here we are towards the South Pole. So in those regions here, you can basically, you cannot swim at the early months and the late months, but you can basically swim around June and July, so in the summer. So for example, Sweden is somewhere here. You can only swim during summer sometimes. And when you go towards south, it's a little bit the inverse. You cannot really swim in June and July. It's colder. And you can maybe swim during early and late months. And towards the middle here, you can basically swim during any time of the year. So if you go, for example, to regions like Sri Lanka or Maldives and so on, you can swim basically at any month of the year. So this is our data set. And you can see clearly that these classes cannot be reasonably separated with a linear classifier. If, for example, you train a logistic regression classifier to this data, then it will perform poorly. Okay, it turns out that decision tree offers a natural way to partition the space into different regions and isolate those classes in different regions. And just as a side note, in this example, we are showing only two classes, but decision trees can really be used for any number of classes. So it can directly be used for multi-class classification where you have more than two classes. But just in this example, we are using two classes just in order to simplify the explanations. Okay, so decision tree will partition this space into several regions. And we say that decision tree is a top-down, greedy, recursive partitioning approach. It is top-down because we start with the overall region and then we gradually partition it. And it is recursive because each new region that we get is again partitioned into subregions and so on. So this is done recursively. And it is greedy because at each step we want to pick the best possible partition. We will see how later. So let's now define what a decision tree is. A decision tree contains nodes. And at each node we ask a question. Based on a feature, for example here, latitude, and a threshold value, for example here, 20. So we are asking this question, is latitude larger than 20? And this splits the space into two regions. So this region and this one. This one contains all the data points where the latitude is larger than 20. And this one contains all the data points where the latitude is less than 20. Now here we are at another node where we ask another question. So in this case, we are at this upper region where the latitude is larger than 20. And we are asking the question, is the month larger than 4? So we are taking again another feature, the month, and a threshold 4. And we are splitting this region into two more regions based on this question. And we can continue to split the space into more regions by asking these questions recursively until we split the entire space into individual regions. So we get this corresponding decision tree. And at the leaf nodes, we have the corresponding predicted classes. So we can now use this decision tree to make predictions. For example, if we have a data point here, let's call it X, we can then start at the root node and ask the question, is the latitude larger than 20? The answer is yes for this data point. So we go here, and then is the month larger than 4? So for this data point, the answer is no. So we go here and we directly predict the class, the negative class. So you cannot swim. So that's basically how you use a given decision tree to make prediction for a new test data point. But now let's see how to construct such a decision tree based on a training dataset. So let's start with the root node. So this corresponds to the entire region initially. And given this region, we want to ask a question here that allows us to split this space or this region into two more regions. So we are looking for a split which depends on a feature j and a threshold t that allows us to split the region R into two more regions. Let's call them R1 and R2. Now suppose that we decided to do this split. So we picked the feature latitude and the threshold 20. We will see later how we decided to pick this feature and this threshold. But by picking those, we split the region R, the entire region, into two more regions, R1 and R2. So this corresponds to this split here. And now we repeat the same thing recursively. So we take this subregion, it's now our region R, and we want to split it into two more regions, R1 and R2. So this corresponds to asking a question at this node here. So we need again to pick a feature and a threshold in order to split this region R into two more subregions, R1 and R2. And if we pick, for example, this feature month and this threshold 4, so we are asking the question, is the month larger than 4? This corresponds to splitting this region R into those two regions based on the month. Now the most important question is how to choose those splits. Or what question should we ask at each node? In other words, how to pick the feature j and the threshold t at each node in order to split the current region into two more regions. Suppose that we want to ask a question at this node. So this is our current region R that we want to split into two more regions. So what feature j and threshold t should we use in order to ask a question here and split this region into two regions? To answer this question, let's try a couple of possibilities. Suppose that we choose to ask this question using latitude and threshold of 50. So we get this split here. And the two regions R1 and R2 that we will get are impure regions. They are impure in terms of label. This means that they contain a mix of different labels. So this is not good. This shows that the question that we asked here, or the threshold and the feature that we picked here, are not good because they led to impure regions. Let's try another feature and threshold. So we are asking now, is the month larger than 6? So this corresponds to splitting the region R into two regions based on the month. So again here, we obtain two subregions R1 and R2 that are impure in terms of labels, because each of them contains a mix of different class labels. So again, this is not a good choice. Now, if we try to ask a question based on the feature month and the threshold 4, so we are asking, is the month larger than 4? So this corresponds to this split. So this gives us those two regions, R1 and R2, and this seems to be a good choice, because at least the region R2 in this case is not impure. Because that's what we want to do. We want to minimize the impurity in the subregions that we get. So basically at each node, which corresponds to a region, we want to find the feature j and the threshold t that splits this region into two more regions, R1 and R2, such that the impurity of R1 and R2 is minimized. But before doing that, let's define how to measure the impurity of a given region. Now suppose that we are at a given region denoted by R, for example this green region here, and we want to compute the impurity of that region. So this is denoted by IR, the impurity of region R. To do that, let's first define PC as the proportion of examples in a region that are of class C. For example, if we are talking about this region, then P plus is the proportion of examples in this region that are of the plus class. They belong to the red class. And P minus is the proportion of the negative examples in this region that are of the negative class. So here there are 7 positive examples in this region among 25. And 18 negative examples among 25. Okay, so given this, we can now define the impurity of a region. And this impurity can be measured by two things. The first one is called entropy. This is the first measure. And the second one is called the Gini impurity or Gini index. Both of them are measures of impurity, so you can use one or the other. That's fine, but I usually use the Gini index because it looks easier. It's easier to compute. So this plot here shows how those two measures looks like. So the blue one corresponds to the entropy impurity, and the orange one corresponds to the Gini impurity. So this is measured with respect to different values of P plus. So in this example, we have only two classes. So if we have two classes and P plus is equal to 0.5, then P minus is also equal to 0.5, right? So for example, if we are at this region and half of the examples in this region belongs to the positive class, then the other half belongs to the negative class. And in this case, this is a very impure region because 50% of the examples belongs to the positive class and 50% belongs to the negative class. So that's why the entropy as well as the Gini index gives very high values. So when P plus is equal to 0.5, this indicates that this is a very impure region. And if the region contains only positive examples, so P plus will be basically close to 1, then the impurity decreases, right? It's close to 0. Same thing, if the region contains only negative classes, then the impurity also is close to 0. So these are the measures we can use to measure the impurity of a given region. Let's now see how to use the impurity in order to find the best split at a given node. So we are at a given node, meaning a given region R, and we want to split this region into two more regions, R1 and R2. So we want to find a split. In other words, we want to find a feature J and a threshold T so that the impurity of the subregions is minimized. So here we define this as the weighted average of the impurity of the subregions R1 and R2. So here IR1 means the impurity of region R1, IR2 is the impurity of region R2, NR1 is the number of examples in region R1, NR2 is the number of examples in region R2, and NR is the number of examples in region R. The region R is the union between R1 and R2. So NR is NR1 plus NR2. Okay, so this is a weighted average of the impurity of the two subregions. Why don't we just compute the average? Why don't we just do IR1 plus IR2 divided by 2? Well, this is because the two regions can have a very different number of examples. So that's why we use a weighted average. Okay, so we are here, and to minimize this, we can just use a brute force search over all possible features and thresholds. So we try to ask the question based on a feature month and various thresholds. Initially, all those thresholds, so we will have n thresholds. And each time we compute this impurity of the subregions that we get. And we try also the feature latitude with various thresholds, so all those. And same thing, each time we compute the impurity of the subregions we get. And we continue. If we have more features, we do that for all features. And at the end, we pick the feature and the threshold that led to the minimum possible impurity, or the weighted average impurity. So suppose that this was the feature latitude and the threshold 20. So we have this split. Now let's take this node, which corresponds to this upper region, and we want again to find which feature and threshold to use in order to split it into two more regions. So we do the same. We pick one feature, for example, the month, and we try it with different thresholds. And here we have much less thresholds to test because we are talking only about data points belonging to this region. Okay, and each time we compute the impurity. And we try also the other feature with different values for the thresholds. And each time we compute the impurity. And we find that this is the feature and threshold that led to the minimum impurity in the subregions that we get. So we use this. Same thing here, we want to find which question to ask at this node. And this one corresponds to this region now. So again, we do the same. We pick a feature with different possible thresholds, and each time we compute the impurity. And then another feature with different thresholds, and each time we compute the impurity. And we will find that this is the combination, or this is the question that minimized the impurity. So we use this split. So just to summarize, at each node we want to ask a question. And we do that by picking the feature and the threshold that minimizes the average impurity or the weighted average impurity in the subregions that we get. Instead of minimizing the impurity in the subregions that you get, you can find some people who try to maximize the information gain instead. So the information gain is defined as the impurity of the overall region R, for example, all this region here, minus the average impurity of the subregions of R. So the average impurity of those two subregions. So basically that's the same. Either you minimize this or you maximize this minus this. So this is exactly the same thing. So if you read some book and you find them talking about maximizing the information gain, then you know what it means. It's the same as minimizing the this average impurity. Until now, we talked about decision trees for classification. But trees can also be used for regression, and these are usually called regression trees. Let's take the same example as previously. But instead of predicting whether we can swim or not, let's say that we want to predict the water temperature. So this is a regression problem because what we want to predict consists of continuous values. These are not classes or categories. So this is our training set. And those numbers here indicates the output, the temperature. Here we also want to split the entire space into individual regions, similar to what we did previously. So we get the same kind of tree, but the leaf nodes now do not consist of classes. Instead, they consist of the average output of each region. So for example, if we take this region, any data point which lies in this region will have this predicted output. And this output is just the average output of the training data points we have in this region. And to construct the regression tree, we do the same thing as what we did previously, but instead of using the impurity IR, the impurity of a given region R, Instead of this, we use the mean squared error. So for a given region R, this sum here goes over all the data points or all the outputs in that region. For example, if we take this region, then we're talking about those values. And this y bar R is the average output in the region R, so the average of those values. So basically this is the difference between each output in that region and the mean output in that region. So that's what we use instead of the impurity. Now let's talk a little bit about some pros and cons of decision trees. First, a decision tree is naturally multi-class, so it can be directly applied to a data set which contains more than two classes. Decision tree is also simple. It is easy to explain even to people who are not experts in machine learning or data mining. And it is also interpretable. So you can easily explain why the decision tree made a prediction for a given data point. So you can convert this to a set of rules, for example, saying that the prediction was this because the first feature is larger than 3 and the second feature is less than 5 and so on. So you can easily convert a decision tree to a set of rules. But we will see later that with other models, like for example neural networks, it is much harder to interpret why the neural network made a given decision or a given prediction. Also, decision trees are generally fast, both for testing and training. So if depth here indicates the depth of your tree, then at test time, the time complexity is just in the order of the depth of your tree. And generally, the depth is smaller than log n, where n is the number of data points in the data set. So if you have a balanced tree, then the depth is bounded by this. So predictions are quite fast. And for training, the complexity is in the order of n times d times the depth of your tree. And d here indicates the number of features in your data set. And this is also quite fast, given that the depth is smaller than log n. However, a decision tree can have a low predictive accuracy. And this is especially the case for data which looks like, in this example, B that we have here. So if we take this first data set A, then it's very easy to separate those two classes using a decision tree. In fact, the decision tree will just contain one node which says that, which puts a threshold on this feature x1, right? So if x1 is larger than 0, then predict this class, otherwise predict this class, and that's it, done. But if we just rotate this data set a little bit, like here, it is very easy to separate those two classes using a model like a linear model, like for example, logistic regression, just by drawing a line here. But for decision tree, you must ask a lot of questions, so you'll get a lot of nodes before being able to approximate this line correctly or sufficiently well. So you need to ask a lot of questions when you have data which looks like this. And even by asking a lot of questions, as you can see here, we don't get a very good approximation of the line. So just by fitting a single decision tree to this data, it can have a low predictive accuracy. The other problem is that decision tree can easily suffer from overfitting. So imagine that you have a very deep tree, so the depth is very large, is very high. So you will split the space into very small regions, right? And at the extreme case, maybe you will have a very deep tree, and then you will end up with just one data point in each region. So this will be a very pure decision tree, meaning those regions will be very pure. So you minimize the impurity. But this decision tree might not be good when you apply it to new unseen data. So we are talking about overfitting in this case. Okay, now let's see some ways to try to avoid overfitting and also to increase the predictive accuracy of a decision tree. So as we just said, it is easy to overfit with a decision tree. If you have a deep tree, which splits the space into a lot of small regions, then you will get pure regions, but this tree is only good on this training dataset and it will not perform well on new unseen test data. One way to avoid overfitting is to define a minimum leaf size. So this will be a hyperparameter. For example, you can say that when the leaf reaches or when the node reaches 5 data points, then we stop. We don't split it anymore. Another way to do this is to define a maximum depth of the tree. So for example, you can say that your tree should not be deeper than 5, for example. Or another way to put this is to say that we define a maximum number of nodes, right? Because by reducing the number of nodes, you get a less deep tree, right? You reduce the depth of the tree and you split less. So you will get larger regions. Or another way is to do pruning. So here you grow your tree too much, okay? And then at the end, you start pruning it by removing, from the end, you remove the nodes. And the way to do that is to use a validation set and each time compute the accuracy of the decision tree after pruning. So all those can be hyperparameters that you need to tune. But the most important thing to increase the predictive accuracy of decision trees and to avoid overfitting is to use several trees. So instead of fitting one tree to this data set, we actually fit an ensemble of several diverse trees. So we have an ensemble method, and this is called random forest. So now instead of just one tree, we have a forest, several trees. So let's see now how random forest works. Random forest is one kind of ensemble methods. An ensemble method combines several models to achieve a higher accuracy. And to do this, the individual models within the ensemble must be diverse. In other words, they must make different kinds of error. Okay, so the members of the ensemble should be diverse in order to complement each other. Now, one way to construct a diverse set of models is to use something called bagging. So to do this, you have your data set, and based on this data set, you generate M data sets or bags. So you do that by sampling randomly from the original data set. You pick randomly data points from the original data set. And also each time you pick a different set of features, right? A different subset of features. So by repeating this random sampling M times, you will get M data sets. And then what you need to do is just to train a machine learning model on each data set. So you will have basically an ensemble of M models. And then once you get new test data, to make predictions about this data, you use all the members of the ensemble and you make the final prediction based on a majority voting. So for example, if there are 2 possible classes and then you have 10 members of the ensemble, so if 8 members of the ensemble made prediction, output the prediction for class A, for example, then you say that the majority of voting is A, so we predict class A. And that's it. Now, what is a random forest? It's just an ensemble of several diverse decision trees. So the members of our ensemble consists of decision trees. And to build those decision trees, we use bagging, as we said. So here you have your original data set, which has n examples, n data points. and they are described by D features. And using bagging, you can create several versions of this dataset. So you will get those bags, several bags. So you pick randomly a number of data points, let's say n prime less than n, and then you pick randomly a subset of features, let's say d prime less than d. Same thing here, you pick randomly a subset of the data points and features, and so on. And then for each data set, you fit the decision tree. So you get an ensemble of decision trees. And then once you get a new test data point x, you predict its label, its class label based on all the trees, and then you take the majority label, right? So you perform a majority vote. And you can also get some confidence about your prediction. So you can predict the probability that a given data point x belongs to class C. And you compute this just as the proportion of trees that predicts the same label C for the input x. And here you can just see an example where you have a data set with multiple classes. And here we have just one tree that we fit to this data set. But here we have a random forest with 100 trees. So just based on one tree, you can see that the decision boundary is not well defined. And we can do better with a much larger number of trees. So in practice, when I want to do classification, I never use just one tree. I always use a random forest.